spent the previous chapter building workflows that execute tasks with perfect repetition. Agent number 9 managed complex state machines, routing approvals and logging audits. But it operated blind. It executed the process, but it did not interpret the information flowing through its own pipelines. Here, we cross a threshold in our architecture. We move from systems that simply perform tasks to systems that reason over empirical evidence. We arrive at agent number 10, the data analysis agent. Looking at the agent taxonomy, we leave the orchestration tier and open the cluster dedicated to data analysis and reasoning. Legacy analytics struggle because they are brittle. If you build a static business intelligence dashboard, it answers the exact query you wired it for. But the moment a user asks a follow-up question that steps outside that predefined schema, the dashboard breaks. Even when those systems generate complex statistics, they suffer from the black box problem. The software spits out an isolated metric, an R-squared value of 0.62, without providing the context of what that number means or the uncertainty hidden behind it. You get a calculation, and you are expected to trust it blindly. To make enterprise data actually useful, we have to close the gap between querying raw information and achieving true understanding, and we have to do it within a single conversational turn. We achieve this by shifting the burden of technical syntax from the user to the machine. You no longer need to know how to write a SQL join or configure a Pandas data frame. You only need to know the right business question to ask. We engineer this agent to act as an R-squared translator. It stands between the numerical data and the human operator. When the mathematical engine outputs an R-squared value of 0.62, the agent translates that abstract math into a concrete decision. It tells the executive, marketing spend explains about 62% of the variation in revenue, and the correlation is statistically strong. But we cannot ask the language model to perform this math itself. If you ask a top-tier LLM to calculate regressions directly on raw database access, accuracy plummets to roughly 16%. However, when you provide that same model with a secure semantic layer to execute proper code, accuracy approaches 100%. We build this accuracy by strictly dividing the labor. The non-deterministic language model is used entirely for intent parsing and planning. The actual mathematical heavy lifting is delegated to deterministic libraries. Decoupling the reasoning process from the calculation engine is what makes a language model reliable enough for production data science. We execute this decoupling through a 6-stage cognitive loop. We replace the traditional black box of analytics with a glass box, an architecture where every analytical decision, code, and anomaly is entirely visible. This diagram maps the data analysis architecture. In Node 1, the LLM extracts the user's intent to create an analytical plan. In Node 2, it translates that plan into executable SQL code. Then in Node 3, it executes the script in an isolated, secure sandbox. Passing the query through a secure sandbox is the structural bridge that turns a standard text-generating AI into a reproducible computational workflow. Returning to our map, the loop enters the post-execution phase. Node 4 is the statistical reasoning layer. Here, the system uses numerical libraries to run OLS regressions and applies z-score thresholds to identify outliers, explicitly quantifying the dataset's uncertainty. Underneath the hood, the Python implementation calls the stats model's API to fit the regression, while simultaneously isolating any row where the absolute z-score exceeds 3.0. This code translates raw data into a statistical defense. By calculating exact p-values and standard deviations, it separates valid trends from random environmental noise. Computation is useless if the operator cannot trust it. The agent must articulate its exact level of confidence to the human making the final decision. This decision tree illustrates how the agent selects the best visual format. If the query involves a timeline, it automatically generates a line chart. For categorical comparisons, it routes to a bar chart, and defaults to scatter plots for correlation queries. Back on our main graph, we reach Node 6, narrate and refine. Notice the dashed line looping back to the start. When the user requests a change, this feedback reactivates the entire cycle, rewriting the code and updating the chart in seconds. This continuous refinement loop takes a static data pull and turns it into an ongoing collaborative conversation between the human operator and their data. In a production environment, this architecture democratizes self-serve analytics. It accelerates data analysis, taking workflows that require hours of coding and completing them in minutes. Teams use these agents to continuously monitor data streams, automatically flag anomalies and customer churn, and generate plain language reports on performance metrics without waiting for an engineering ticket. But we must establish a hard boundary. Agent 10 is a strict interpreter. It reasons only over the explicit tabular data it is provided. It does not go out and gather its own evidence, nor does it have the capacity to design and run physical, real-world experiments to prove its hypotheses. The data analysis agent is a flawless executor of mathematics, but its final insight is entirely bottlenecked by the integrity of the underlying data. If you feed it biased or incomplete numbers, it will confidently return a biased and incomplete insight. This exposes the system's critical vulnerability. Because this agent makes definitive statistical claims, those claims must be independently audited before a business uses them to make a high-stakes decision. This chart of our 30 agents shows exactly where that auditing happens. Right next to the data analysis agent sits agent number 11, the verification and validation agent. It is designed to check the factual consistency and logical coherence of every claim generated. To examine the exact Python implementation for the data analysis agent, read Chapter 8 of 30 Agents Every AI Engineer Must Build by Imran Ahmad. The book is available now on Amazon and Pact. You can access the complete architecture codebase, deployment guides, and visual maps used in this episode at neuralsca. Mastering the data analysis agent allows you to take the raw oil of enterprise data and refine it into a high-performance engine of verifiable truth.